This podcast was produced from a webinar. For a more interactive experience with visuals, visit advancedmanufacturing.org/webinars.
Hello and good afternoon. My name is Susie Marzano, and I'm the Senior Manager of Technical Community Strategy and Engagement at SME. Welcome to the Manufacturing Edge webinar series. The title of the webinar is Efficient Inspection and Real-Time Quality Monitoring for Ultra-Precision Polishing of Inertial Confinement Fusion Shells. The research presented today was awarded Best Paper at NAMRAC 53. And now I'd like to introduce Barbara Linke, the lead of the Manufacturing Edge webinar series, who will introduce our speakers. Barbara.
Thank you so much, Susie. I'm very happy to introduce today our two speakers to you. So Professor Satish Bukar-Patnam is a Regents Professor and the Sugar and Mike Barnes Department Head Chair of Industrial and Systems Engineering at Texas A&M University. The second author and co-presenter is Shashank Gala, Graduate Research Assistant at Texas A&M Engineering Experiment Station, also at Texas A&M University. So without further ado, please, I invite you to the stage.
Thank you. Thank you, Barbara. Thank you, Susie, for giving us this opportunity to be part of this Manufacturing Edge series. First of all, howdy and good afternoon, everyone. And as Barbara introduced, I'm a faculty member in Texas A&M. And before I begin, I wanted to acknowledge the works of my students, current students Shashank, and my former students Akash, Bhaskar, Yuhav, Samson, and Sai Kiran. It's because of their work and their diligence that we have some of the things that I'll be sharing with you. In terms of the presentation, I will be following this outline. One of the things that is central to everything that basically defines this work is the needs of nuclear fusion, that is ICF experiments. I will try to provide a background to this ICF experiments and then how our research gets contextualized in this frame. Next, I will talk about the ultra-precision ultra-precision finishing as well as its quality needs, both in terms of inspection and real-time monitoring, and then provide some perspectives on the process designs before I summarize this presentation. I would assume that this talk would be less than half an hour in its duration, and then we can take a lot of question and answers. Let me begin by introducing this whole work about this inertial confinement nuclear fusion. You may recall in December of 2022, the Lawrence Livermore National Lab made an announcement of what we call as ICF breakthrough. For the first time ever, they were able to realize more energy from a nuclear fusion experiment, a controlled nuclear fusion experiments, than the energy that was input into the system. And they call it a successful ignition. And what this experiment consisted of is placing a shell that you see here. It's almost like a BB gun ball, well finished. You put it in a chamber called a Hall round, which is about a few centimeters in dimension. And you hit that the circular ball filled with all the isotopes of hydrogen with about 200 lasers, very powerful lasers. And if you hit it right, if everything goes well, it would create a particular Rayleigh-style instability that releases X-rays at a particular type of energy levels to cause a nuclear fusion reaction. That is, hydrogen atoms combine to form helium. Right? So what you see in this bottom picture is basically a graphic of multiple lasers hitting the shell of the fuel capsule simultaneously to release this energy. And all that we have been working with the Lawrence Livermore lab relates to the finishing of the shell. The shell is about 2 millimeters in diameter. And what you see on the right-hand side is basically the actual photograph of some of these shells that were used for these fusion experiments. And for these shells to disintegrate well, to release the right kind of X-ray and then cause fusion reaction, they need to have very precise surface quality. And in fact, the quality of these shells is considered to be the critical component determining the success of an ICF experiment. And how this surface of these shells are prepared, they basically go through a series of polishing steps to realize almost specular surface finish. The roughness should be about 5 nanometers or less, very high sphericity, and also the surface defects, especially pits, should have volumes no greater than 3 cubic micrometers. And also, the shell is made of a diamond-like carbon type material, and the thickness of those shells should be within about 1 micrometer. So they are you're trying to think about a precise shell with very high surface quality. And the process of making, essentially you take a silicon mandrel, basically silicon balls, so to speak, coat it using a PLD-like process with diamond-like carbon. Basically, it actually goes through multiple layers of different kinds of materials, but the top shell is mostly a carbon. And then you go through a very rough lapping type process called tip truncation to remove all the rough surfaces. What you see in the micrographs are the surface morphologies that you get to see at the end of coating, the tip truncate, then regular lapping process, polishing process to get the final surface. And essentially, you're not only controlling the finish, but also you're controlling the geometry as well as defectivities during the course of entire polishing steps. So you're controlling material removal rate, finish, and defectivities. And you are doing it over a series of steps. For example, the lapping and polishing, every step consists of using like a batch of about 20 shells that are polished using mostly like mechanical abrasion. And they actually have like 15 to 20 different stages of lapping and polishing. So essentially you take a shell, you basically run it through almost like rough lapping. Then you basically start with regular lapping to ultrafine abrasive polishing, about 15 to 20 different stages of these polishing steps. Each step can go from anywhere from 8 to 24 hours. So it's like a slow, laborious process. And after each stage, you take the shells out, the entire batch of about 20, and then inspect them for defects. Right? And it's very much a time and resource intensive. It's time and resource intensive. But when you inspect, you're not only inspecting it for dimensions and surface quality, but mostly you're kind of looking for process anomalies that leave out some of these unnecessary defects. These defects that are most deleterious or harmful are the surface pits. As I mentioned, your pits should not be of volumes greater than 3 cubic micrometers. And these pits typically form due to those grains that were kind of PLD'd onto the surface getting pulled out. And it can happen due to some anomalous motions of the shells within the polisher. So we kind of need to track to make sure the surface quality is preserved. In addition to that, there are other anomalies like cracks and process failures that you need to kind of watch out for. And as mentioned, all these defects, as well as the process detail, like so many steps, like 15 to 20 steps, each stage consisting of about 24 hours. It's like a long drawn process with very strict quality requirements. And right now, as we stand today, getting these shells ready is one of the limiters to the scale up of these ICF experiments. We cannot have enough number of shells of the right quality produced at the rate that would sustain an ICF type experiments for generating realistic scale power. Right? So among these, this presentation addresses the issues related to dealing with the surface quality from the standpoint of inspecting efficiently to look for these surface bits, which are considered to be the most harmful. And also look at the process in real time to identify anomalous motion that are highly risky and can yield some of these defects. So essentially, we'll talk about this whole thing in the context of inspection of the shells at the end of each stage, and how do you do it efficiently? Because as I mentioned in the previous slide, for each stage, you are looking at 17,000 scans per batch. It's like hours together to inspect. So we want to reduce that. How do you do it efficiently? That's something that we will be talking about. And that's the work that was presented in the last NAMRAC conference. In addition to that, 2 years ago, we presented a work on real-time monitoring. We have done an additional effort beyond what we presented 2 years ago to identify some of these anomalous motions that are likely to cause some of these harmful defects. And then I will end this presentation by talking about the process designs with which we can avert or mitigate some of the issues related to these harmful defect formations. Right? So this pretty much is the outline of this presentation today. And what I would like to do is to invite Shashank to kind of give us a little bit of a deep dive about the work on the surface inspection that actually led us to the efficient way to sample the surfaces to assure quality. Over to you, Shashank.
Yes. So I'll start by giving the quick workflow of what we have been doing to efficiently inspect the quality of the shells. So we start with the surface finishing experiments, and once we conduct the surface finishing experiments, like let's say polishing or lapping, then we take surface scans, and we take surface scans using the Keen's machine. And once the surface scans are taken, they are processed to get the pit informations. So in other words, we are trying to extract the points in the surface scan where we have high deep and high volume pits, and we try to represent these pits in the form of a kernel density function. I'll more talk about why we are using a kernel density function and why not other traditional metrics like surface roughness or any curve based methods. So to give an intuition of what a kernel density estimate is, KDE represents the pit depth and pit volume in the distribution space. In other words, like when you try to represent all the pits as a KDE, you will get the likelihood of having a high or deep pit. You can like basically choose the threshold, and you can try to get what's the likelihood of having a certain pit with certain characteristics. And like, why do we need KDE? That's one of the question that I wanted to answer. So traditional metrics like surface roughness and all the other measurements tries to average out everything, and it hides the rare defects that we are looking into. So when we are talking about these pits, as mentioned, these pits which are dangerous are considered to be deep and high volume pits, and these deep and high volume pits are tend to be occurred rare, and it's not that usual to detect. So traditional metrics like surface roughness doesn't work out here, and other curve based method doesn't give us the joint information about different characteristics of the pits. Let's say we are considering depth and volume, it doesn't give information about it. So KD as a overall, it's a better representation of the pit characteristics. And KD, to summarize, KD provides a complete distributional level representation of surface pits and capturing the rare and criticality of the pits as well. So now I will talk more about how do we obtain these KDs and how do we obtain the surface scans, and where that's the important crux of this work. So once we do experiments and get a surface scan, we do image processing to these respective surface scans and we get the pit masks. Once we get the pit mask, we construct a KD using the pits identified from these pit masks. And how we do it using the equation that is shown here. In other words, we'll get all the points that are there in the surface and we try to construct a Gaussian kernel around this and try to represent these pits in form of a joint distribution. I'll not go much into the details of the math, but I would like to give an intuition of how do we obtain the KDE given a surface scan. And so the beauty of this representation is that for a particular batch, you can have just one KDE representation, and this one KDE can tell us information about what's the probability of having high and deep volume pits, such that we can easily tell that a particular batch is good or not using this single representation. And that's why like KDE can be an important quantifier in quantifying the pit characteristics, specifically the depth and the volume. So now that we know that KDE can be a good representation for an entire batch, the next question that comes into our mind is how many scans that we need to accurately represent a KDE for a given batch. This forms the crux of this work, and this is the main idea. Like, how can we efficiently sample? How can we efficiently do the inspection sampling such that we get an accurate representation of the entire defect distribution? So to answer this question, we use an inequality called DKW inequality. So this it's quite prominent in terms of statistics. We solve this equation to get number of pit points that we need that can accurately represent the distribution of an entire batch. And how do we get this number of points is by solving the equation that is shown here using a fixed point iteration algorithm. And once we define a particular error rate and the thresholds for a batch to be accurately represented and solve this algorithm, we get particular number of points called n number of points is needed to accurately represent the pit distribution. I know this information is a bit overwhelming. I would like to again give a brief overview of the sampling scheme, how we can process things. So first, we have to decide out on the error rates and the thresholds on how much we can allow the error for a particular batch. Let's say like 5% error, 3% error, depending on the design choice and depending on the stage. We first decide number of what's the error that we can allow, and we give these numbers to the algorithm, and this algorithm points out to number of pit points that we need to accurately represent an KDE. So now we have theoretical number of samples and where we can confidently tell that okay, we can have a good KDE using this number of data points. So in order to attain this number of data points, we first take a scan and we extract the pit points, and we check if the number of pit points is less than or greater than the number that the algorithm gives. And we do repeat this process until we reach n number of points that the algorithm gives. In other words, we will try to take surface scans until the number that algorithm points out, and those number of surface scans are enough to tell that a particular batch of shells have accurate pit density characteristic distribution with some error predefined error rates. I hope this is clear, and this entire process helps us to determine the minimum number of scans that is required to accurately represent the pit density distribution given the error rate and the confidence level that we choose in the start of the process. So we also have an algorithm to validate this approach. So we try to validate this method. So we started with a particular batch, and we choose the error rate of 3% and significance value of like 1. And we got around, the algorithm gave us around, like we would be needing around 7,900 points in order to accurately get a right representation of pits. And we did take surface scans until we reached this number, and we took around like 6 surface scans where we could get around 8,900 points. So when we try to construct the distribution between 7,900 points and 8,900 points, these distributions match closely to each other, and we validated it such that after 7,000 points, we tried to add iteratively each point and see if the distribution is changing drastically or not. And the method converges for 7,900 points, and which is like practically validated with the experimental readings as well. So in other words, this says that okay, this method is particularly working in representing the pit density characteristics distribution. So we theoretically derived the sample size, and we have performed experiments to validate this theoretical number, and it worked out pretty well. So all we need to do is we need to take those many number of surface scans in order to reach the number which the algorithm points out. So again, like when we try to compare the distribution, probability distributions of what the algorithm gives and what's the total number of surface scans we have, they pretty much closely match each other, and we can confidently say that whatever the number that algorithm gives are sufficient to represent KDE as a good distribution for the entire batch. And we also did check the variations across the batches, and it is found out that things are like consistent across batches as well, to see okay whether it's working for one particular batch or whether it's working for other batches as well. So it's pretty much consistent, and we see the expected trends in the results. As in the graph, we could see in the initial stages which are lapping, so we expect to see a deep pits, we expect to see high volume pits, and as the things progresses, we expect to see these things gets reduced, or the probability of observing deep and high volume pits are reduced. And the expectation, or like whatever the hypothesis we started with, it's been validated using the method that we followed, and we see a promising in this method for an efficient sampling scheme or like inspection to identify the bit density distribution. So in short, like to summarize, so this approach, like where we try to achieve like accurate representation of kernel density estimate of bit density characteristics, which is the depth and the volume. And this method tries to we validated it on a particular batch. It worked really well, and we try to generalize it across batches as well. It tried to capture the expected trends that we see, and on a whole this can be one of the efficient sampling scheme which helps us to reduce the inspection time significantly rather than spending more time on taking detailed surface scans. So now I will move on to the real-time monitoring part, and this work like has been like presented in NAMRAC 2024. And I'll talk a bit. I'll also talk about our current work, like which has been accepted to this year's NAMRAC. So continuing on where I stopped on efficient sampling scheme. Now that we have seen like a KDA can be a good quantifier for representing bit characteristics for a given batch. Now the next question that comes into our mind is, can we predict the KDE given, okay, let's say given the information of next stage, you can polish it or lap it for like certain amount of hours, or you can change you can give all the input parameters which the polishing or lapping depends, and the current stage KD information. The question is, can we predict the next stage KDE? And why do we need to predict is the most important thing. If we were able to predict, we can enable early detection of undesired outcomes, which means that we can weed out the shells that can result in poor quality. So let's say you have the current stage KDE and you know what the next stage is going to be, and if you can predict that, okay, even though the next this is the current state of the batch and the prediction yields little bad, we can like try to weed out the shells, or we can stop we can change the polishing or lapping parameters, and we can efficiently come up with some strategies to improve the quality. That's the whole idea of why we need to predict. And also, like as I mentioned, we can come up with different polishing or lapping strategies. Let's say we can change the polishing time, we can change the polishing parameter settings, the speed at which the polishing happens. All these things, we can try out different things and see how the next stage results look like, and we can proceed with the outcome that is more promising, which in turn saves a lot of time and cost. So, and achieving the next stage prediction is a very challenging task. And why it is challenging? Because as Dr. Mukhopadhyay mentioned in the start, the process is very stochastic in nature. So it's a multi-stage processing, and like each stage the time is not constant. So the time keeps on varying, and things are like not consistent with respect to the stages. And the next main challenge is that the process is non-stationary. As I can say, like early lapping stages, they have a higher material removal rate, and the later stages they have like low material removal rate. So it's kind of non-stationary. So it's hard to learn between the process and the distribution relationships. And more importantly, the pit evolution is non-linear, and some pits gets removed during the process and some new pits get formed, and it's hard for us to predict what the next stage would look like. But given the recent advances with AI and machine learning, we try to propose a deep learning method which is known to handle all these challenges really well, to forecast the next stage distribution given the current stage information. Let's say whether it might be what would be the next stage, polishing, lapping, time information, process settings, and we can predict the next stage bit density information. And this will enable us to determine the defect distribution earlier, and we can improve on process control. So I'll quickly skim through the methodology. I will not go into much detail. Again, like we do polishing experiments, we take surface scans and we convert them into pit masks, and we obtain KDE from the pit masks, and we give both KDE and process information to a deep learning model, and the deep learning model can predict the next stage KDE. So in short, like to summarize, we combine both the KDE and the process information, which is fed into a deep learning model. In the back end, it uses a mechanism called cross attention mechanism, which is very popular with all the LLMs that we see, all the chat GPT. It uses the same cross attention mechanism, and we use the same mechanism here to learn the relationships between the process and the defect distributions. And we do have like customized loss functions to address the non-linearity, non-stationarity, and pit evaluation challenges, which I have discussed in the last slide. Skimming through the results, on the right-hand side, we could see two graphs, two columns. The first column is the ground truth KDE of the next stage prediction, and on the right-hand side, it's the predicted by the model, and the predictions visually capture it really well. By just looking visually, they tend to capture the trends of the pit distributions really well. And we also validated using empirical metrics, using some statistical metrics called KL divergence, Wasserstein distance, and they turned out to be really good. I'm sorry, due to the space constraints, I couldn't put the values here, but I just want to show that this method is working. It is confirmed both by visually and numerically as well. And once we know this model, the immediate question that comes into our mind is how this model can be utilized, how well it is able to identify deep and high volume pits. In order to do it, we did a small numerical study. So where we choose like a thresholds of like, okay, for deep and high volume pits, and we asked the model to predict what is the probability of having a deep and high volume pits and what is the probability of having a no pit. And the model did pretty well in identifying deep and high volume pits, and it's almost working like 14 out of 16 cases it predicted well. But for the predictions of no pit, the model did a decent job, but it gave us more false positives as well. And which is a good thing for our case, since the quality requirements are very standard, and we need a conservative threshold on this regard, so that we do not miss out on any deep or high volume pits. In other words, the model is working pretty well in identifying deep and high volume pits, and at the same time it's trying to be more conservative on identifying no pits as well, which is good, and so that we don't miss out on any deep or high volume pits. So to summarize, we try to show up some, we try to forecast the next stage pit distribution using a deep learning model, and it worked out pretty well, and which in turn helps us to identify the shells that can lead to undesired outcome, and it can help us come up with some polishing strategies where we can optimize the process. So now I will move on to the monitoring process anomalies. As mentioned in the start, shell interactions are known to be one of the key drivers of pit formations and formations of shell cracks. So in order to identify these process anomalies, we have sensorized the polishing machine with a video and a vibration sensor, and we collected the data, we analyzed both the video and vibration data. We found out to be there are like multiple shell interaction events that we see, and out of these multiple shell interaction events, there are like prominent shell interaction events, and these prominent shell interaction events are classified using the momentum transfer that's happening between both the shells. So in short, like, we try to calculate the velocities at which these shells are moving, and we try to quantify the momentum transfer between both the shells during collision, and we try to classify the events based on this and the vibration energy signals. It found out that we were able to capture the signals in the vibration energy. We were able to capture the signatures in the vibration signal pretty well when these prominent interaction events happen. So let's say when the shells are interacting, and if they tend to be like a prominent interaction event, which means that there is momentum transfer that's taking place, and we see a spike in the vibration signal. And this is our the work that has been presented for NAMRAC 2024. And yeah, to summarize, we have tried to present our work on reducing the inspection time. So where we try to come up with some efficient sampling strategies which can help identify the pit density distribution accurately, and which can help us reduce the total inspection time and cost. And we have talked about predicting the kernel density estimation using current stage information and current stage kernel density estimate. And the outcome, or the main why it is useful, is that it can help us weed out the shells that result in undesired outcome, and it can help us come up with some efficient polishing or lapping strategies which help us to optimize the process. And we are currently working on the design aspect. We are trying to learn the process and the quality relationships to come up with polishing or lapping recipes. So the main goal is to achieve the desired surface quality while minimizing the polishing time and minimizing the costs related to polishing. I think that's the end of this presentation. Any questions? Questions are welcomed.
Thank you so much. I see one question from the audience. What kind of instrument is used to measure surface scanning parameters? Something like a scanning electron microscope?
No, actually, we don't need that level of precisions and resolutions. Basically, different kinds of very high precise optical profilometers, including some of the things that you see from Keynes, are sufficient for scanning the surfaces.
Thank you. So if I'm looking into, or your research is treating the shells in a batch, like 20, you said 20 shells in a batch. How do you, or would you assume that the distribution is similar throughout the batch, or do you see one shell really bad and the
It's a
others?
great question. So you are sampling only a subset of shells within a batch. And also you are sampling very small portion, less than 5% of the surface area of a shell, even within a subset of the batch, right? So that is the beauty of what we have been trying to accomplish. And you're taking such a small fraction of the complete surfaces that needed to be scanned, right? We want to kind of look for those rare anomalies. It's not just coming up with understanding the curve alone, but we want to estimate the tail of the curve, the extremely rare events of those pit formations that need to be tracked. So that is the gut of the challenge that we tackled. So what we have assumed in this whole thing, right? Because assumptions lead to results, I guess. So what we assumed is the shells in a particular batch, they emerge from the same batch right from the inception, right from when the mandrels are made into the PLD, and then all the lapping and so on. So we kind of keep the batch together so that they can be statistically consistent. In other words, we only are looking at a small subset of shells every single time. And even within those small subset of shells, we are actually randomly scanning only small portions of the surface, essentially about 5% of the entire surface area. So yeah. So that actually helps out a little bit, because the time it takes to search for those basically rare events can get drastically reduced. Having said that, the technology is advancing to a point where these shells are getting to be, it's very expensive instrument, but you can actually rotate the shell 360, both in phi and theta. And then you can come up with more efficient and much more rapid scanning, but that work is still underway. But for now, this efficient scanning kind of reduces a lot of cycle time.
Awesome. But you still have to transport the shells to the measurement device.
Yes, absolutely. Yeah. But these shells are brittle, but they are not too hard to handle.
Do you think there is a future for some in-process inspection or in between the processes on the machine?
Yes, absolutely. In fact, as you can see in those videos, it's not easy to observe the shells while they're getting polished, right? Yeah. And we are working on it. In fact, our work is actually focused on getting the resolutions to a point where you're not only tracking the rectilinear or linear motion of the shells, but also the spins as well as the complete motion patterns of those shells. Then we can get to the extent of trying to capture how the surface is getting modified. But I think it will be, to give a complete outline here, we've been working with them for the last 6 years now. First 5 years, it's part of one LDRD. Last year, we began another LDRD, the second project. The second project focuses precisely on the point that you raised, Barbara.
Awesome.
Look at how we can track some of these things in situ and be able to monitor the surface modification.
Yeah, I've seen a follow-up question was coming in on the sampling strategy. How does the sampling ensure we get realistic estimate for the whole population, possibly some statistical methods?
Yes, exactly. That's our attempt was to come up with a statistical quantification of determining that number, that is, number of scans we need. And this statistical quantification is based on a DKW inequality that Shashank presented. But even that inequality actually contains a few assumptions. But for now, these assumptions seem to be okay. And once we come up with a conservative number, we are able to reduce the number of scans. But a lot more statistical developments are needed to make it all work.
Awesome. One other question, can you tell a bit more on the signal to noise and uncertainty in raw data before you put it into the model?
Oh, yes. The surface scan information, interestingly, is quite precise. The instruments have a resolution of, they claim like a few nanometers, right? So for microscale pit determination, it's not too bad, especially if you want to look for these rare but deep pits. We don't miss too many of them from the scans. But when it comes to vibration signals as well as in situ monitoring, noise becomes a very, very important factor. As you can see here, it's pretty much a blur in terms of how the shells move relative to the camera. So luckily, there are some AI methods that are being developed in the last 5 years, focused on retrieving the motion of fast-moving objects. Shashank's work is focused on leveraging some of those advanced computer vision methods to deal with the noise in the vision systems. Of course, on vibrations, of course, you need to really understand the time frequency characteristic of the spectrum to consider the right time frequency chunks that will be indicative of changes in the process. Again, understanding of this process-machine interaction is important as you kind of figure out which one's useful and which one's nice.
Mm-hmm. Yeah, awesome. While you were doing the analysis, did you see specific sensitivities towards the process step? I mean, yeah, you showed a little bit about what was going on when you had lapping and then polishing. Seemed to have different probabilities for those. Was it for the pits?
Yeah, pit probability or probability of finding those rare pits. Yes, absolutely. You see, the chance of a pit formation reduces drastically as you go from lapping to polishing.
And in the future, there's hope to improve the process, right? That's what you said.
Yes. Yeah.
Short.
Absolutely. In fact, that's what we are working on. Once we understand how the surface is getting modified, then we will be placed to come up with the right kind of adjustments to the process. Otherwise, we are just tuning purely based on the statistical information. It will have some positive effects, but that I think by understanding the process, I think we can do much better.
Is there a future production number that is or I mean, yeah.
Yeah, absolutely. In fact, I can share the vision of some people as to how this ICF or Inertial Confinement Fusion would be deployed in the future. Again, this is all dream, but we can talk about it as a vision of some great minds. So right now, there is the shell that's held in an hall round, and then lasers are precisely coming and hitting it to generate this fusion reaction. In future, the vision is to kind of release these shells like they are coming from a gun, release like millions of them, and then have these lasers come and hit them so that you generate sufficient power that would kind of will be useful for real world applications. Right now, we are looking at improving the success of this ignition, that is realizing more and more power or more and more energy from a single hit. We started with about 2.2 meg, and now we are close to 10. So that's, and then over time, I think it will improve. And as you can see, the latest news, which was released not too long ago, basically shows a significant step improvement in the ignition success compared to the original breakthrough. So we are hoping that by hardening the various components, shell being one important one, and there are other things also, our LLNL NIF group will be able to succeed in taking this technology to the next level.
Wow, that's really exciting.
Yeah, it's definitely exciting because it's a form of energy.
Right. Everything with those two small 2 millimeter balls there.
Yeah.
Very cool. Yeah, maybe one last question if no more come in, but please, if the audience has more questions, type them in or yeah. I'll see. I was wondering, do you have other applications in mind for this measurement and measurement method and calculation protocols? Do you think other polishing processes or other machining processes? Or
yes, absolutely. The KDE method is definitely applicable to various rare anomaly detection scenarios. In many cases, you can have a fast process cycle time, but inspection becomes a bottleneck.
Yeah.
And all the time, when you're looking at inspections, you're looking for that rare defect you want to kind of not ignore. And that's where this method would be very helpful. All other applications, most of the things like dimensional analysis, quantification, and general inspection, it's not so useful. But when you're looking at rare anomalies, you're spending a lot of time inspecting and looking for it. I think this is where it's going to be helpful.
Sounds great.
Yeah.
Awesome. Yeah, thank you so much.
Thank you again. Thank you so much. And I hope it was informative. And again, thanks to SME and Edge for inviting us for this seminar. I hope everybody enjoyed as much as we did sharing what we have.
Yes, thank you so much, Satish and Shashank.